Thank you for coming to our talk. Welcome. As you can guess from the title, we're going to be talking for the next 45 minutes about robots. So let's first start to understand what an industrial robot is. Because we might have seen this, we might have seen some pictures like this, but you may imagine that there is a lot of complexity behind these machines. So to take off some of the complexity, we reduced and simplified the view that is necessary for this talk. So there are standards, mostly ISO standards, that specify and define the architecture of industrial robots. So they're mostly standardized. What you can see at the center of this image is, of course, the robotic arm, right? So it's made of metal most of the time. It's very heavy. It has multiple joints, and all the joints are motorized. There are several servo motors that allow the arm to perform very complex movements. At the end of the arm, there is what is called the end effector, which is essentially the hand of the robot. It might be a cutting device, might be a set of pliers, might be a laser or other welding equipment. It really depends on what the task of the robot is. So these robots are generic. They can do everything. That's why they're interesting. So the end effector can be changed depending on the application. On the opposite side, we see the human, the operator, which is the one that, as you can imagine, moves and interacts with the robot by using a certain device that we will see in a minute. In between, there is what is interesting for us from a security perspective and, of course, for attackers. It's the controller. If we open the box of the controller, we actually literally open the cage of a controller, what you see on your right, you see a bunch of computers in there. The main one is called the main computer, and it is the one that has most of the interfaces with the external world. The first component that needs to be attached to the main computer is the teach pendant. The teach pendant, you can imagine it as a very rugged tablet with a joypad on it, with which the operator can interact with the robot directly. So it can literally use it as an extension of his brain, of his arm, sorry. After that, after instructing the robot to perform a certain movement, in between there is the axis computer. The axis computer is the one that translates a movement as a high-level command as an axis movement. For example, move a certain joint 30 degrees left, right? This is still a high-level command, and in order to be actuated, we need another intermediate device, which is the drive unit. That's the one that translates an axis movement into a drive for the servo motors. For example, apply a certain amount of power to servo motors 1 and 2 for a certain amount of time. And this creates the actual movement. Great. So one of the main characteristics of industrial robots is that they are flexibly programmable, in the sense that you can write code as you were writing code for another application, by which you can instruct the robot to do the same task, to perform the same task over and over. These programs can be written from scratch with a normal editor, or they can be recorded as macros using the joypad. So you can turn the robot in teaching mode, do some movements, and then you can repeat the execution. An interesting thing of these programs is that they are implicitly parametric. You can imagine that in order to perform a certain complex movement, there is a lot of physics behind it. There is a lot of kinematics behind it. So the controller is actually solving a control problem. What we tell to the controller is move a certain joint to a certain position. But behind it, the controller has to solve the problem. How much does the arm weigh? How much far do I have to go? So to reach a target, there is a certain amount of control problems that need to be solved. And all of these are implicitly parametric, so that the programmer only needs to write a program and the controller does the rest. So if the physics of the system changes, the program will automatically adapt. And this is interesting because it makes the robots very generic. Of course, it also opens a possibility for repercussions. So if these parameters are, for example, I'm just giving you a hint, saved in a configuration file, if the configuration file is altered, this might end up in a wrong movement, the robot not being able to reach a target in an optimal time. Great. So second characteristic of industrial robots is that they are connected. That's why we call them industrial robots connected robot, so to speak. If we take a look at one of the, not previous generation, but not bleeding edge robot by Comau, for example, they were already meant to receive commands in a very interesting way. You can send emails to the controller and the robot will execute a command, or you can have the controller send you emails in order to give you monitoring signals and stuff like that. So they are already meant to be connected, even if you're not looking at the most, latest generation of robots. In addition to emails, there are, of course, other protocols that can be used to program and interact with these robots remotely. For example, we have found that in ABB they use FTP as a mean to upload code or upgrade the certain components. But of course, there are also other non-standard protocols. For example, ABB uses this API to receive commands, and the newest generation, they also have a REST-like API. So they're getting more and more open. And all of this is sitting, as you can see, in a pretty wide attack surface, from simple USB ports to Ethernet ports, even radio devices. What you see with the little antenna that you see on the right is a 4G modem. So there are various reasons why you want to connect your robots, from simple monitoring, which is even specified in the standard, from active control of the production. This is what we are expecting in the near future. At the end, we might expect, it's not very hard to imagine a future where there will be app stores or library stores where even industrial operators can download pieces of code and compose them together to create a complex task. There is even already an app store for consumer robots, so it's not really hard to imagine that at some point in the future there will be app store for industrial robots as well. So given all of these premises, and given that robots are so connected, I'm asking a question, and I'm asking actually to one of my colleagues. Do we believe that cyber attacks against robots are, a realistic threat? What do you think, Davide?
Thank you, Federico. We answered this question to the users of our survey. So we interviewed 50 domain experts between industry and academia, and we found out that the 20 of them that replied, a little bit more than half of them, thinks that a cyber attack against an industrial robot is not a realistic threat. So we asked them also a bunch of other questions. For example, what are the consequences that you foresee if an attacker has compromised your robot? So most of them were worried about the impact on physical safety. Is the human operator at risk? Some of them worried about production losses. What if the attacker stops the production plant? One of them even hinted, what if the attacker inserts some small defects in the products? So the other question that follows this one is, of course, then what are the most valuable assets at risk? Well, they are, of course, intellectual property. On the controller, there's code that is specific to a certain production. So this might be part of the intellectual property of the business. But they also cared for humans and for materials and equipment. So, as you have seen in the last few slides, the impact is way much more important than the vulnerabilities alone. So, how can we assess the impact of an attack against industrial robots? Well, we can start reasoning about the answers that the users of our survey gave us, but we should also think of the requirements that an industrial robot should have. So what are these requirements? You can think of them of something close to the laws of robotics of Asimov. In fact, the first one is safety. The robot should never harm the user. The second one is accuracy. You can see on the image there's a robot that has been programmed to throw a dart right in the center of a dartboard. To do so, this robot must not only locate the dartboard, so have some input from the physical world, and it must do this accurately, but it must also throw the dart correctly. So we have a twofold requirement of input and output accuracy. The third and last requirement is integrity. What can go wrong? What can go wrong is that the user, or the malicious user, can ask the robot, for example, to reach a position which is not physically reachable. The robotic arm can break, for example. So if such a command has been sent to the controller, we should avoid that such a thing can happen. So a robot-specific attack is a digital-born violation of these requirements. We developed 5 of them, and the first one is the one of control loop alteration. So as Federico told you before, these robots are pretty much flexible. We found out that usually there are configuration files that stores some of these implicit parameters that describe, for example, the control loop properties and the kinematics, the values of the kinematics parameters that are used to calculate the next position. So what if an attacker can modify these config files? What happens is that after the compromise, the user will send a command, try to execute a program. What happens is that since the representation of the physical world for the robot has changed, something weird can happen. We developed a proof of concept to show you what will happen. We weren't able to bring the robot with us. It didn't fit in the luggage, but let me show you the video. So in this video, we show you how we programmed the robot to just draw a straight line, nothing fancy, extremely easy. At this moment, the robot is not under attack. Again, try to think of this from the user perspective. Now, the robot is under attack. Nothing changed. The code is always the same. What you will see is actually that something is happening. From the user perspective, the operator perspective, still nothing has changed. Did you notice anything? Well, if we look closely at the pencil trail, we will find out that a small drift of a couple of millimeters has been introduced. This, modulo of course quality assurance processes, can have a devastating impact. The next attack is the one of calibration tampering. Not only the robot should know, let's say, the representation of the physical world, but it must be also able to calculate an error and account for this error in the representation. So you will have to calibrate the robot. What if the attacker is able to compromise again the calibration parameters? What can happen is that either he is able to again introduce some micro defects or damage physically the robot, the motors. The third attack is the one of production logic tampering. In this attack, the attacker is able to compromise the safety requirement. He does so by modifying the code, for example, that is running on the controller. In this image, you can see that we've written wrong density. You specify the weight of the object that the robot is picking in the code. If the attacker can change this representation, some fancy things happen. You will see, for example, the robotic arm started drifting upwards. So if the attacker is able to compromise the code, to modify the code, because no code integrity checks are present via a man-in-the-middle attack, he is able to do basically whatever he wants. Modify the production process completely, introduce micro defects. He's free to do whatever he wants. The last two attacks are the ones about the state alteration. What if the attacker is able to modify the state of the robot, turn it on at his will, or change the representation of the state that is displayed to the user? Well, if the user reads motors are on the teach pendant, he will not enter the workspace. If the attacker has compromised the robot, we have seen that he can, sometimes he can change the state of the robot, or at least he is always able to change the information that is displayed to the user. So in this case, the user will read, motors are off, free to go. Instead, he will be at risk. We developed a proof of concept also for this attack by introducing a malicious DLL in the teach pendant. And as you can see on the interface, the teach pendant is saying to the user, the robot is in manual mode, you need to move the joystick to move it, he will go slow, and the motors are off. Don't worry. What is really happening instead is that the robot was in automatic mode, it can go fast, hit the user, do whatever he wants, and the motors are on. So this raises an important question. Is the teach pendant part of the safety system? The answer is no, because there are safety standards in place that mandates that if the user enters the workspace of an industrial robot, for example, he enters the cage, an emergency stop must be issued, and the robot should stop. But as we have seen many times, what is mandated by the standards or what is the best scenario is not what happens in real life. So what if these safety measures are too limiting? We asked it to our users. Some of them replied, yes, well, these measures are kind of limiting for us. So what do you think they will do? Well, they will customize them. Most of them said, yes, well, we did something with our safety measures. We changed them in some way. So what happens if they change the measures in some weird ways? This mail was a follow-up to our report, and a researcher described an incident where they were running a security scan of the network, just a normal nmap ping scan, and one of the packets happened to wake up the PC that was controlling the robot. The robot started swinging at full speed, and the only physical safeguard that was there, well, was just a red line drawn on the floor. Fortunately, no one was hurt. So, as we've seen, things in the real world can change a little bit from what we expect. Up to now, what I described requires an attacker to be in control. So, how can we do this?
Thank you, Davide. So, up to now, we assumed that the attacker is able to compromise the controller from a remote standpoint. In this second part of the talk, we will try to lift this assumption, and we will describe how we managed to find a couple of vulnerabilities that actually allowed us to remote compromise the controller. We didn't perform a complete vulnerability assessment. Our goal was just to implement those attacks that we explained before, and also all the vulnerabilities that I will explain you after that have been fixed or mitigated by ABB or by the vendor of the robot. So let's go back to the attack surface of the robot. As we told you before, the main point, the main component of the robot controller that exposes the most attack surface is the main computer. The main computer exposes a lot of network services, and it is the component that is the gateway between the external world and the controller. So we focused our analysis to the main computer. From a technical standpoint, the main computer is an x86 system running a real-time operating system, VxWorks. A second component that is extremely interesting from our point of view, because it is the gateway between the user interface and the robot, is the Flex Pendant. The Flex Pendant is another embedded system which runs Windows C. So let's go back to the main computer. The main computer, as we said, exposes a lot of network services. Those network services are authenticated using a user authorization system framework, which is a kind of standard user authorization system framework where every user, human user I mean, authenticates using a username and a password, and it is used to authenticate the access to all kinds of network services. Each user belongs to a set of roles. Each role belongs to a set of permissions. If we go back to the user manual, we see that there is actually a default user with a default password. From new versions of Robotware, from Robotware 6.04, it is actually possible to deactivate the default user, and it is actually suggested, not in the user manual, but in the deployment guidance that are given to every robot customers to deactivate the default user. So even if we get network access to the robot, we will need to compromise the controller to bypass this authentication. One point of view, one subsystem that we can look at to find vulnerabilities is the update system. So to update the system, as the system is composed by a lot of computer-based components, you just update the main computer. Then the main computer will transmit, will propagate the updates to all the systems. For example, when the Flex pendant boots, it will fetch the software that it needs to run from the main computer. And it does this using FTP. When you boot the system, the Flex pendant connects via FTP to the main computer and will download the code. There is no code signing, so if you are able to change the piece of code that is stored on the main computer, you will be able to change the firmware running on the Flex pendant. The point is, how is this authentication performed? Well, before the latest patches, the Flex pendant authenticated to the main computer using any credentials. Basically, the user authorization system was turned on after the Flex pendant booted, so to allow the Flex pendant to actually download the software update before a user could actually type a username and password, because the boot is unattended. The update system is not the only subsystem where we have a kind of complex interaction, complex unattended interaction between different components. Another interesting point is the auto-configuration of optional components. This is a service box, is a gateway using for remote monitoring. Federico will talk about this later. And this service box can be plugged into the main computer via Ethernet and will auto-configure itself automatically. Again, the auto-configuration is performed using FTP. And this time is performed using FTP and hard-coded password, because there is no way to type password inside the service box before the first auto-configuration. Fortunately, those hard-coded passwords will allow just to retrieve files and store files in the /command subdirectory. The /command is actually a driver which allows to perform two operations: read system information, the version of the software running on the main computer, the current timestamp, and all kind of information, and execute commands. If you store a file in /command, this file will be actually parsed by the command driver, and some commands will be executed. For instance, when you connect the remote service box to the main computer, it will upload the file to auto-register itself. So you can see remote service registration with a certain IP address that is the IP address of the remote service box. So it is interesting to see what commands do we have at our disposal. And it turns out that we have a shell command. The shell command takes a single parameter and executes this parameter as a VX work symbol. So basically, you can execute any symbol in the main computer firmware using shell and the name of the symbol. Unfortunately, it is not possible to pass parameters, so we can just execute function without parameters. But there are interesting things that we can do. We can do a reboot, shell reboot. Or worse, we can disable the authorization system. Shell UAS_disable will completely disable the authorization system. And given the fact that we found a hard-coded credential to access this driver, we have remote command execution, limited by the fact that we cannot pass any parameter. But if we look further in how the main computer parses the parameters, parses the commands, we see that we have an unbounded right to the stack. So the parameter, the name of the parameter is just copied straight to the stack without any boundary check. We have a straightforward memory corruption vulnerability. We have a stack overflow that will allow us to perform remote code execution and basically execute arbitrary code on the main computer firmware. This is not the only, let's say, parsing routine or security critical routine. We also found stack corruption vulnerabilities in other points. One is in the parsing of the RobAPI protocol. There is an unsanitized string copy from a parameter of the protocol to the stack. And also in the case, we can have remote code execution. Or also in the boot of the Flex pendant. In the code that manages the boot of the Flex pendant, there is still another buffer overflow that will allow us to perform a denial of service, for instance. So this is just a subset of the vulnerabilities that we found. And the takeaways of this is that we were able to find some standard memory corruption vulnerabilities. Stack overflows, unsanitized copies, nothing particularly fancy, and nothing particularly difficult to fix. Most of the vulnerabilities that we found are logical vulnerabilities. It is a complex system. It is a complex distributed system with different subsystems that are different microcontrollers, different processors, and those need to communicate together. And the implementation of some part of this communication was flawed from a security point of view. But the main problem in our vulnerability assessment is that all the components are blindly trusting each other. There is no hardware or software trust boundaries between different services running on the main computer or different hardware components. So just a single stack overflow vulnerability in an unknown, poorly audited, not so important service of the main computer, and you can compromise all the components running on all the robot controller because the components are trusting each other. So to wrap up, we are able now to completely compromise the controller. Just connect via FTP or connect via Rob API and exploit either the static credentials and remote code command execution or one of the memory corruption that we found to execute arbitrary code on the main computer. Once we can execute arbitrary code, we can call the function to disable the UAS. Once we disable the user authorization system, we are now able to upload and download arbitrary files to the main computer storage. The main computer storage is basically used via FTP as a shared file system for all the components. Now we can, for example, upload a malicious DLL that will be executed at the next boot by the Flex pendant. This DLL can straightforwardly implement the attack that Davide showed you before, the one about state alteration, or can, for instance, implement some kind of command and control or per-system functionalities. So at this point, we can actually say that we have the robot controller completely under the attacker's control. There is a small step missing because to implement many of the attacks that we showed you, we need to tamper with configuration files. Configuration file that contains sensitive parameters, for example, the PID parameters, the parameters that control the kinematics of the robot arm. And as those files are sensitive, those files are encrypted. Actually, those files are obfuscated more than encrypted. And by reverse engineering the robot controller firmware, we were able to reverse engineer the obfuscation, which is kind of simple, and tamper with the files. So we are now able to, from a remote standpoint, to connect to the robot, exploit the robot, run arbitrary code, and tamper with the configuration file. So basically, we have all the elements in place to implement the attack that we showed you before in the video. But we need to connect remotely to the main computer. So the question is now, is it actually feasible for an attacker that is not working in the company, that is an external remote attacker, to actually connect to the controller, to a robot controller, and launch our attack? So let's go back to the problem of connected robots.
I know how to do it. So now we go in a little bit more in depth into how robots are connected. We only glanced at the beginning. So if you're looking at the modern factory, pretty much this is the scenario that we have in mind. There are several connection points. Some robots will be connected directly to the internet via their radio interface through custom APN, for example. It really depends on the vendor. Some of them will only be connected to the computers in the LAN, in the factory LAN, and some other will be indirectly connected to the internet using a normal gateway, like a basic case. This scenario is also fairly confirmed from the small survey that we run. It's not very surprising to discover that most of the domain experts that we asked, they use Ethernet to connect the robots. I personally found it a bit surprising to find out that they were using Wi-Fi to connect to the robot. I mean, within the factory LAN, I don't think it's a great idea because I mean, a simple vulnerability in the radio firmware might end up having the attacker within reach, even if it's outside the factory, right? So another question that we were curious to know the answer of was, do you connect your robot also directly to the internet? Because we were really interested into this. And fortunately, only a minority of them told us that they would connect the robots directly to the internet. So the next question is, so given that these people are, some of these domain experts are telling us they do connect robots to the internet, are we going to find any robots if we simply scan the internet for them, right? So this is the results of a Shodan scan actually reflect what we got. Fortunately, we haven't found a lot of exposed robots. If you simply search for the top 5 brands, this is what you're going to find. I checked a couple of days ago, and there were 10 more than that. But we've been monitoring these searches for about 1 year, and all the numbers that we got were, flowing between 25 and 35. So not a lot of them. So actually, if you change your point of view, instead of looking for the robots, you look for the brands of the routers that are used to connect these robots, you're going to find a much interesting picture. We searched for the 12 top manufacturers of industrial routers. We haven't focused on generic network equipment manufacturers such as Cisco, simply because they produce a wide variety of products. We focus only on vendors that produce specifically industrial routers. So the first thing that stands out from this slide is the amount of routers that you find. Clearly, not all of them, there isn't an ethical way to verify which of these are actually connected to robots, as opposed to generic industrial equipment, but it gives a picture. It's a superset, but still includes the number of robots connected there. Because some of these vendors, for example, E1, are the vendor of choice by the robots vendor. E1 is used by ABB. Other vendors are used by, other routers are used by other robot vendors. So they do include the number of robots connected. Another thing that you notice, the right column, is that some of them are even connected with no authentication enabled. So the second red flag is that there is a deployment issue. I mean, there are configurations that are not secure by default in these devices. You might wonder how we found all of these devices. I mean, if it was easy or not to find these devices exposed, how we crafted the search pattern. Well, unfortunately, it turns out that it was rather easy. I must say unfortunately, and I'm going to explain you why I mean unfortunately. What you see at the bottom there is one probably extreme example of a vendor that thought it was a good idea to expose a very verbose network banner. And this is actually common among these vendors to announce, details in the network banner. So generally, I mean, this is not even a vulnerability. Probably, if you talk to the vendors, you can tell them that there is an info disclosure kind of vulnerability, but it's not an extreme case of vulnerability. But still, I cannot really find a use case for exposing, in this case, even the frequency of the CPU, the MAC address of the network card, the date in which the firmware was built. What else? The serial number of the device. I cannot honestly find, maybe I'm overlooking something, but I cannot find a use case for that. If you find it, please, I will be happy to know that. So this is a general issue that we found in most of the devices that we have analyzed. Most of them are very, very verbose from a network banner point of view. So if it were devices connected to non-critical equipment, one would say, okay, fine. I mean, this simple vulnerability is not of high impact. But in this case, I mean, these devices are connecting industrial equipment. I cannot really find why an industrial equipment would need such an exposure. So here, of course, don't get me wrong. I'm not advocating in favor of security through obscurity. Of course not. That's a bad idea. But of course, if there are vulnerabilities, the response shouldn't be to hide these devices. The response should be fix those vulnerabilities. But on top of that, you also have to make sure that these network banners disappear, because you're simply making the attacker job easy. You craft a simple search on Shodan, and you can find all of these devices plain easy. Not that these devices are not vulnerable. I mean, they are vulnerable. We and other researchers before us found that a good majority of these have outdated software stack. The main components in these devices, you might imagine, it's a Linux kernel, some BusyBox, and SSH, and probably a web server. If you find that even this small set of software is outdated, then it's not a very good picture that you have. Even crypto libraries sometimes were outdated, and the firmware of the baseband was outdated in some of these devices. So given that they are used to connect critical equipment, again, they should be more and more focused. Also, the web server sometimes is vulnerable. This is an example that I wanted to bring because it's kind of funny. There is this vendor who has plain copied the code from a beginner's blog explaining how to create a REST API in PHP, copy and paste into the router. And the vendor response was, well, this component is not exposed. OK, fine. But then there is zero input sanitization. I'm simply showing a short snippet, but believe me, there's no input sanitization in that. And the code is copy and pasted directly from a beginner's blog. So I didn't really I wasn't very, very happy when I found this. So the bottom line through this example is that when you need to connect your robots, use some care. And as Marcello told you before, the robots vendors are providing you guidelines that you're not going to find online on their website. They're going to give you a separate manual, a separate security manual that you have to use to properly secure your deployment. And they offer guidance. I mean, this is what one of the vendors told us. They offer guidance specifically for connecting robots to a network or to the internet directly. So now I think we have a lot to wrap up. So I'm going to hand the slider to Davide, and then we'll go through question and answers.
Thank you. So let me conclude this talk. I hope you enjoyed it. Let me just wrap up what we said, give you some more insights. So we have seen in this presentation that robots are being increasingly connected. This can pose a problem. We developed some industrial robot-specific classes of attack, and this happens also because these robots are extremely flexible. The barrier to entry, fortunately, is quite high. I mean, an industrial robot can cost at least $75,000 used. But, of course, we know that this isn't the barrier for a motivated attacker or for an attacker with the financial means. What should we do now? We've seen that the vendors are very responsive. We were extremely happy to work closely with ABB, the vendor of the robot. They fixed the vulnerabilities in no time. Were extremely available also to help us verify our findings. So this was amazing. But we feel that as a community, we really need to push for countermeasures. So let me give you some hints on what we think should be the countermeasures that we need to implement in the next few years, maybe. So as a short-term countermeasure, we think that we should work on the user side. We need to implement attack detection and deployment hardening. So we are talking about the user side. On the vendor side, instead, as a medium-term objective, we should think of system hardening, integrate secure development in the life cycle of the applications. But what we think is the most important point, probably, is that you remember a couple of years ago, there were no security standards for the automotive field, right? So same thing happens for industrial robots. We have safety standards. They are also amazing, but they do not take care for an active attacker. So we hope that our research will shed some light, give some hints, so that new standards can be born regarding the security of industrial robots and not only the safety aspects. You can find our contacts on top, and the papers, slides, and every material are on robosec.org. And the second link is our industry report. So if you have any question, feel free to ask